Alright, welcome back. You ready? Let's do this. So again, the property-based set describes all elements of type A which satisfy a property. Basically, in math terms, we say element X in domain A such that property X. All right, this is the mathematical canonical definition of the property-based set. Okay, now let's go ahead and implement all of our methods. So not apply, because that's the general contract of my set, but let's implement all the methods here. So I'm going to delete all the lines and I'm going to implement all the methods in turn. Now, before I start implementing, if you want to take a break and implement these functions yourself, I highly encourage you to do it, because we've gone really far in defining potentially infinite property-based sets. So go ahead and implement these functions yourself. They shouldn't be really too bad, and I'll come with solutions after you unpause the video. So let's start with contains. When is an element contained in a property-based set? Well, it's contained in a property-based set if the property holds. So the implementation for contains is just going to be property element. Just like that. Next, adding an element. When do we add an element to a property-based set? Or in other words, what kind of property do we obtain after adding an element into a property-based set? So if you take a second to think about this, if we say X in A with property X, and then we add an element, then we get the set with X in A in the domain such that property X or X is equal to element. Right, so that should be the implementation of our addition method. So let me move this above and actually align it so that we have proper comments. Document your code, people. And in the plus method, I'm just going to say that I'm going to return a property-based set with A, where the property is that for an X in A, I'm going to return property X or X equals element. Okay, so this is basically the mathematical definition in Scala syntax. Cool, let's apply the same style of thinking when concatenating, quote unquote, adding or unioning with another set. So this is going to return a new property-based set where for any element X, the property X is going to hold, or another set contains X. Now, I should also put an equal sign here so that I don't confuse the compiler. All right, so if you think about this, this is a similar mathematical definition. So if I concatenate this property-based set with some set, that means I get X in A such that property X or the other set contains X. All right, and this is the equivalent Scala implementation. All right, now mapping, flat mapping, and filtering I'm going to avoid for a second, and I'm going to implement a small method called politely fail that will just throw an illegal argument exception. And I'm just going to say really deep rabbit hole. That's the case with map and flat map, because I cannot really map and flat map a property-based set because I don't know what I am going to obtain. We can easily get into the situation where from all integers, by mapping with mod 3, for example, we can get into the set 0, 1, 2. But the problem is that once we get into that, we won't know that this is actually a finite set, and we cannot really test if a number is actually in the set. Take a second to think about this. If you map an infinite set with a function, you will not know whether the resulting set is finite or not, so you won't be able to tell if an element is in the set or not, which breaks basically the whole point of a set. So I'm just going to say that map, flatmap, empt for each are going to be implemented with politely fill. All right. Really sorry, guys. This is how math and computer science, unfortunately, in this case, work. All right. Filter, on the other hand, is much more interesting because we can create a new property-based set with A, where for every x, I'm going to say property x, or actually and predicate x. So I'm going to hold only the elements for which both the property and the filtered predicate hold for each element x. Now I'm going to keep this for later for now, the removal of an element. I'm going to implement this really in a really sweet fashion in just a minute. So let's go to the intersection because it's very familiar to us from the non-empty set, and we're just going to use filter. And we're already done. The difference is also very straightforward, and we're just going to say filter not another set. And we're also done. And the unary bang operator for a property-based set will just return a new property-based set of type A with the opposite property, such that for every x, the opposite property holds for x. All right. So if you have all the property-based set of integers with even numbers, the unary bang will return all the integers for which the property of evenness does not hold for the numbers. So you'll get all the odd numbers. Now, removing an element will just be implemented in terms of filter, where for any element x, x is not equal to the element that I'm passing in as a parameter. Think about this. So this is a really cute and straightforward way of removing an element from a property-based set. Just filter out all the elements that are equal to the parameter that I pass in. All right, so take a step back and take a deep breath and evaluate the code that we've written for the property-based set. This is kind of complicated, but it practices a different way of thinking about collections. And here we went into a deep rabbit hole with potentially infinite functional sets. So having defined a property-based set, we can go back to the empty set and non-empty set and implement the unary bang operator as a property-based set where for any element x, I'm just going to return true. So I'm just going to put in an underscore here because I don't care about the name of the parameter. So this is basically the all-inclusive set that we wanted to instantiate at the beginning. So as you see, the property-based set is much more flexible, and we can define multiple property-based infinite sets by just passing in a property here. And the all-inclusive set is just this expression right over here. And for the non-empty set, if I define, where is it? The unary bang operator. Okay. This will return a new property-based set where for every x, that's just not this contains x. All right, so quite a chunk of code, people. Let's go to our little test code and see our code in action. So let's create a negative, which is not s. So that is rewritten, of course, as you know, to s.unary bang, which is now all the naturals not equal to 1, 2, 3, or 4. So let's print out some tests here. If we say negative with the value 2, then this number 2 should not be included in the set. But if I print line negative with 5, then this should be included in the set. So I'm just going to see false and true here to the console. So let's go ahead and run this. Compiling. Might as well drink some coffee. And yes, false and true. False means that the number 2 is not in the negative set, but 5 is. Now let's keep all the even numbers just to say negative dot filter and underscore mod 2 is equal to 0 as lambda. And if we print line negative even with 5, then instead of true as we saw earlier, I should get false because 5 should not be included in negative even. Right? So I'm seeing false again. But if I say val negative even 5, which is negative even plus 5, so I'm adding the element 5 back. This is basically all the even numbers bigger than 4. All right, so these guys were included, and then plus the number 5. Okay, if I print line negative even 5 with the number 5, then I should see true back because I've added the element 5 back into the set. All right, so I'm seeing the value true here. So take some time to play around with the other methods, with removing elements, with concatenating, with intersection, with all that kind of stuff. Do not do map or flat map or for each on property-based sets because they will crash in your face because we don't know beforehand whether these sets are finite or not, right? So take some time to play around with the functions that you've written and verify that they work correctly. And in the meantime, I wanted to say that I really appreciate that you stuck with me here in this journey. You rock! I'm really proud of you for making it this far. This is really hard code. But now that we've done it, I really encourage you to play along with it and explore some other open questions that I haven't really gotten to. For example, can you tell in advance if a set is infinite or not? Should a set be given a generator function that generates the next elements of a given property? Can you even do that? Should a set be iterable or not? Do we really need map, flat map, and filter? Why don't we actually design a set as a pure function? And so on and so forth. There are lots of questions that you can explore on your own, and I really encourage you to do it. But I'm waiting for you in the next video where we discuss some more functional collections. Don't worry, I won't put you through 200 lines of more Scala code, but we will put to use the new mindset that we've developed in the last few videos, and we're going to discuss sequences and maps. So I'll see you there.